Black holes are mysterious regions in space where known laws of physics completely break down. First predicted in 1916 by Albert Einstein, black holes were once only a theoretical concept. For decades, no visual evidence existed, making black holes feel like an idea born of science fiction. It wasn't until better telescopes came into the picture that astronomers noticed strange behavior in stars. In the 1960s, something unique was discovered in the Sin star cluster. A glowing blue star was emitting extreme X-ray radiation while circling something invisible in the sky. The invisible object had so much mass that it clearly affected the star's orbit. This mysterious entity was later confirmed to be Cina X1, one of the first strong black hole candidates. Sin X1 is about 6,000 light-years from Earth and shows signs of unimaginable force. Its gravity is so strong that not even light can escape its grip in the cosmos. Because it absorbs everything, including light, it was named a black hole. After this discovery, scientists began finding similar objects across our universe. They now estimate that our Milky Way galaxy has over 100 million black holes. These can be small like those formed from dying stars or gigantic ones at the heart of galaxies. The massive ones called supermassive black holes pull stars and gas around them like whirlpools. Their gravity not only warps nearby space but also shapes entire galaxy structures. Anything that gets too close to a black hole meets the event horizon, a point of no return in the void. Inside this boundary, not even information can escape the pull of gravity. Objects falling in experience spaghettification, a term describing the stretching into thin strands. This stretching happens because gravity pulls more on one side than the other. Like taffy in space, all of it ends at the singularity, a center where all matter is crushed into infinite density. The laws of physics, as we understand them, no longer make sense inside this hidden core. Despite learning a lot, black holes still hide their true nature behind mystery and darkness. They are nature's experimental labs, perfect for testing gravity, time, and the rules of reality. In 2021, the world saw the first real image of a black hole taken by the Event Horizon Telescope. This telescope captured the center of M87 galaxy over 50 million light-years away from Earth. The image showed a shadowy silhouette surrounded by glowing matter in the void. It offered more than beauty. It gave insight into how black holes actually behave in deep space. Scientists found that black holes have three parts: the event horizon, the photon sphere, and the singularity. The photon sphere traps light into orbits like a deadly glowing circle. The center, the singularity, is where the known universe stops making any sense. These structures show that black holes are not just holes but complex systems in the cosmos. Although they share general shapes, each black hole shows unique behavior depending on its surroundings. Scientists can't just point a camera and look. They must study X-rays, gravity, waves, and star motions. We use the motion of nearby stars to figure out the presence and size of these invisible objects. Black holes are believed to form when massive stars collapse in their final moments in the universe. Others might form when galaxies collide, or when small black holes merge into one bigger monster. NASA confirmed this during research of M87's core, showing a supermassive black hole in action. One breakthrough came in 1963 when Roy Kerr proposed the rotating black hole model. His version, known as a Kerr black hole, has spin and introduces a new area called the ergosphere. Inside the ergosphere, space itself gets dragged like a spinning vortex. This effect makes it possible to escape the ergosphere under certain conditions. In theory, this contrasts with the event horizon where escape is impossible in the black void of space. Kerr's idea changed how we think about energy and motion near spinning black holes in the cosmos. Black holes are no longer just fantasy. They're at the center of modern research in physics. They challenge our ideas about time, gravity, and what it means to be real in the universe. Though we can't visit one, learning about them teaches us which we are and where we belong in the stars. Inside a black hole lies a region unlike anything we've ever seen, hidden deep within the void. This exotic place may contain secrets about how the universe works on a fundamental level. One idea is the Einstein-Rosen bridge, also known as a wormhole in theoretical physics. A wormhole might link two distant points in space or even two different universes. This tunnel is based on the belief that space-time bends under mass and energy, like a flexible fabric. Think of it like a folded map with a tunnel between two places far apart on the surface. These ideas sound amazing, but raise hard questions about whether wormholes are actually possible. Theoretical problems include stability, and whether they need exotic matter to hold them open. Even if wormholes were real, Einstein's theories say nothing can travel faster than light in the cosmos. Still, these ideas fuel our imagination, reminding us how much we dream about travel through space. This fascination leads scientists towards something even bigger, a unified theory of everything. Such a theory would combine general relativity, which governs stars and galaxies, with quantum mechanics. One of the top candidates is called superstring theory, which suggests all particles are vibrating strings. Instead of being points, everything is made of tiny strings moving through space. Each string has a frequency like a note, and together they play the music of the universe. This makes the cosmos seem like a giant symphony of energy across space and time. Superstring theory helps explain mysterious things like black holes and wormholes. As these strings interact in space, they create patterns and distortions in reality. However, superstring theory also says there are extra dimensions beyond the for we know in space. These hidden dimensions are so small and tight that we can't see them with current technology. Imagine being a fish in a flat pond, unaware of the sky above. This is how we might miss higher dimensions. Even though we can't touch them, their mathematical signs may explain gravity and mass. These unseen dimensions offer ways to solve puzzles about how particles behave in the cosmos. They also give us clues about how the universe started and how it might one day end. Superstring theory bridges math and physics, creating a new field of deep cosmic exploration. Still, it remains unproven as its ideas are too small-scale for modern tools to detect in labs. That said, string theory continues to inspire scientists to look deeper into reality. In recent years, quantum black holes have offered new insights by merging gravity with particle physics. Edward Witten called string theory 21st century physics that arrived early, showing its depth and challenges. New models now show how black holes might follow string theory rules, at least in simpler worlds. But extending this to the real 10-dimensional universe is still incredibly difficult. As scientists explore further, they dive into the very fabric of reality in the cosmos. The final goal is to unlock the secrets of existence and how everything is connected. Studying black holes is about more than math. It's about changing our view of space and time. They collide with neutron stars, release gamma rays, and drive extreme energy events in the universe.